Hi, welcome to our presentation on matrix chain multiplication. This is by Jack Reboul and Ethan Rue. So the matrix chain multiplication algorithm is an algorithm that determines the most efficient way of multiplying together a chain of matrices. So we can call it A1, A2, A3, all the way up to AN. So we need to find what the most efficient way of multiplying these matrices together to have the lowest cost to multiply them together. So the algorithm determines the order to multiply the matrices together. So for this example, we have matrices A1, A2, A3, and A4. So there are multiple ways we can multiply these four matrices together. So in this first example, we can multiply A1 and A2 together, and A3 and A4 together, and then multiply the result of that together. Or we can multiply A1 and A2 together, and then multiply that with A3, and then multiply the result of that with A4. So there's many different ways that we can accomplish this multiplication, and we need to find out what the most efficient way to do this is, and that's where the algorithm comes in. Let's look at the cost of a matrix multiplication. So just basics, if we're multiplying two matrices together, let's say matrix A and matrix B to get matrix C. So first, to multiply two matrices together, the number of columns in matrix A has to be equal to the number of rows in matrix B, or else the matrix multiplication is not possible. So that's just one of the basic rules of matrix multiplication. And so multiplying A and B together will give you an A by C matrix, so matrix C, which is A by C, and we get that by the number of rows in A and the number of columns in B, and that will give you A by C for the resulting matrix. So this is just an example where A is a 2 by 3 matrix and B is a 3 by 4 matrix. So they both have 3 here, so this is the same, so that checks the property up there and results in a 2 by 4 matrix. So how to multiply two matrices together? So you take the first row of A and the first column of B, and you multiply 1, 1 with B's 1, 1 and add it to A 1, 2 to B 2, 1, and then add the multiplication of 1, 3 and 3, 1, and add all three of those together, and that is the result of 1, 1 in matrix C. So you do here, and that's here, and then this and this column, and that's 1, 2. So you do with this row and all these columns, and that's where you get all the entries for row 1 of matrix C, and then it's the same with row 2 of matrix A. So you multiply all these with here and here and here and here, and then that fills out the entries for row 2 of matrix C. So that's how you get all the entries. So that is a lot of multiplications. So that's the point of matrix of this algorithm, is to determine the best order to multiply matrices together. So in this example, it's just 2, so we don't have a choice, but just looking at the two matrices, we can see the cost of multiplying two matrices together. So for this, we have, just for this one entry here, we have 3 multiplications. So we multiply this and this, and this and this, and this and this. So that's 3 and add it together. So, and there's 8 here, so there's 2 rows and 4 columns. So for each entry, we have to do 3 multiplications. So the total amount of multiplications for A times B is actually the number of rows in column A multiplied by this middle value here, multiplied by the number of columns in matrix B. So the total multiplications for A times B is 24. So that's just what we use going on for the rest of the algorithm. So now we know how many multiplications it takes to multiply two matrices together. Yeah. So here's just the general equation. So if A is x1 by x2, B is x2 by x3, then that means C would be x1 by x3. So the number of multiplications would be x1 times x2 times x3. So now let's talk about the intuition of the matrix chain multiplication algorithm. So this algorithm uses dynamic programming and a recursive algorithm to compute the most efficient way to multiply the chain, a sequence of matrices together to get the minimum amount of multiplications. So the recursive algorithm, so it takes the sequence of matrices and separates them into subsequences. So then it finds the minimum cost of multiplying out those subsequences. And then it adds together, adds those costs together and adds the cost of multiplying together the subsequences. And it does this for all possible times that the matrix sequence can be split. So for an example where we have A, B, or if matrix A, B, C, and D all needing to be multiplied together. So it recursively calls to find the minimum cost of A times B times C, A times B, C times D, and B times C times D. So in order to be as efficient as possible, this algorithm saves the computed answer of the subproblems to make it more efficient to solve the bigger problems later on. So knowing the cost of multiplying A to B together will help you solve the problem of multiplying A times B times C together, and will help you find the minimum multiplication cost. All right, so now let's go ahead and work through a simple example with four matrices, A1, A2, A3, and A4, with the size of the rows and columns listed here. All right, so now we're going to implement the matrix chain multiplication algorithm in this example with four matrices, A1, A2, A3, and A4, with the rows and columns listed below. So for this algorithm, so we've written out two 4x4 matrices, matrix M and matrix S. So they're both 4x4 since we're multiplying four matrices together. So matrix M is where we're going to store the minimum amount of multiplications from multiplying this value with this value. So for example, so this entry 2, 3 will be the minimum amount of multiplications required to multiply together A2 and A3. And in matrix S, this is just how we're going to remember where to partition the sequence in order to get the minimum multiplication value. So I'll explain more of that later. So let's begin with M11. So all the values on this diagonal here is just the multiplication value of multiplying together 1 by 1, 2 by 2, 3 by 3, and matrix 4 by matrix 4. So clearly these are all 0 since they're multiplying by themselves. We don't need to worry about those at all. We can mark those as 0. And all these entries below the diagonal we can ignore because we're not going to be multiplying matrix 2 by matrix 1. We're only going to be multiplying matrix 1 by matrix 2. So all of these we can ignore. We're just going to focus on these, and same goes for here. We're just going to be focusing on these for this matrix up there. So let's start with A1 times A2. So that'll be M12 in this matrix. So let's do M12. So the cost of multiplying A1 times A2, there's only one option. We can't partition this in any different way. So looking back at the equation we talked about previously, so the number of multiplications required will be the number of rows in the first one, multiplied this middle value, and the number of columns in A2. So this will be 3 times 3 times 6. Wonderful. And that is 54. 9 times 6. And in the S matrix, we can just mark this as 1. Okay, so now let's go into M2, 3. So M2, 3, so it's the same, so it would be the number of multiplications required to multiply A2 by A3. So that's 3 times 6 times 2. So 3 by 6 by 2. And that is just 36. 36. And then for this value here, M3, 4, so that's the cost of multiplying A3 and A4, so it'll be 6 times 2 times 4, which is 48. So I'm going to put that in. And for these, I'm just going to go and put 2 and 3, because that's the value that where we multiply it. So this is 1, and then 2, and then 3. All right, so now let's look at M13. So we need to find the minimum amount of multiplications for multiplying together A1, A2, and A3. So for this case, so now we have two different options for ways to multiply these together. So first option, we could do a2 times a3 and then multiply that times a1. Or we could do a1 times a2 first and then multiply that result by a3. So what we need to do is calculate the number of multiplications it takes for each of these cases and find the minimum. And the minimum is the value that'll go as m13. So let's start with this case. So a1, so that's 0 since it won't cost anything to multiply it with itself, plus a2, a3. This is where the dynamic programming comes in and looking at the smaller problem to help solve the bigger problem. So a2, a3, we already solved that. So the cost of multiplying a2, a3, we can go back to this M matrix and look at M23, which is 36. So we can put 36 in here. Now we need to add the cost of multiplying together a2, a3, and a1. So a1's a 3 by 3. A2, a3, so it's a 3 by 6 by 6 by 2. So a2 by 3 will end up being a 3 by 2 matrix. So it'll be a 3 by 3 times a 3 by 2 matrix. So the cost of that will be 3 times 3 times 2. And that is equal to 54. Cool. So now let's look at this one. So as we did before, so a1, a2, we can look at this M matrix and find this value here, which is 54. So 54 plus a3, so just 0, plus the cost of multiplying them together. So a1, a2, it'll be a 3 by 3 times a 3 by 6, so that'll end up being a 3 by 6. So it'll be a 3 by 6 times a 6 by 2. So it'll be 3 times 6 times 2, and that is equal to 90. So looking at these two, we can see that 54 is smaller than 90. So this is the value that will give us the minimum. So we can put in M13, 54. So now to remember that this is optimal compared to this, we need to mark a value in S, in the S matrix. So in S13, so we need to signify that we multiply, so A1 is like what we're multiplying it by, so this is kind of like where the split off is, so we'll mark A1, so we know to like separate A1. Cool. Okay, now let's look at M24 and do the same thing that we did for M13. So M24, multiplying A2, A3, and A4. So this can be done in two different ways. We can either multiply A3 and A4 together and then multiply that with A2, or we can multiply A2 and A3 together and then multiply that with A4. Awesome. So let's look at this example, or this option here on the left, and then we can compare and see which one's the minimum. So let's start with this one. So A2 is just 0, plus A3, A4. Looking at this table, it's 48, and the cost of multiplying them together. So A2 is a 3 by 6, and then 3, 4 will be, so it's a 6 by 2 by a 2 by 4, so it ended up being a 6 by 4. Just look at these outer terms. So it'll be a 3 by 6 times a 6 by 4, so it'll be 3 times 6 times 4. And that is equal to 120. Awesome. Now let's look at this example. So A2, 3. So we can look at this M matrix and find that 2, 3 is 36. So 36. A4 is just 0. And then cost to multiply them together, A2 and A3. So it'll be a 3 by 6 by 6 by 2. So that'll just be a 3 by 2 multiplied by A4, which is a 2 by 4. So it'll be a 3 by 2 by a 2 by 4. So it'll be 3. So it'll be plus 3 times 2 times 4. And that gives us 60. So this option here is more efficient than this because it has half as many multiplications required. So this is the minimum. So we'll put 60 in M24. And since we're splitting it at A3, we're going to mark 3 right here. Excellent. So now we can go on and solve M14. All right, so now we need to find the minimum value for M14. So M14 is the minimum value, minimum amount of multiplications required to multiply together A1, A2, A3, and A4. So this is the final square we need to fill out, and then the algorithm will be done. So we're almost there. So M14, so it has three different options of ways to multiply this together. So first option, you can multiply A2, A3, and A4 together and multiply that with A1. Option 2, you can multiply A1 and A2 together and then multiply that with the result of A3 and A4. Or you can multiply together A1, A2, and A3 and multiply that with A4. So what we need to do is find the minimum value of these. So let's start with this first one. A1 is just 0. And then we can look back at this M matrix to find the minimum value for A2, A3, A4. So that's just M2, M24. So M24 is 60. And the cost to multiply them together, so A1 is a 3 by 3, and then A2, A3, A4, so it's a 3 by 6, by a 6 by 2, by a 2 by 4. So we can just look at these outer terms. So A2, A3, A4 will just end up being a 3 by 4. So it'll be a 3 by 3 by times a 3 by 4, so it'll be 3 times 3 times 4. The value for that is 96. Okay. All right, the second one, so A1, A2, so M12 is 54. M34 is 48. And now we need to add the cost of multiplying them together. So A1, A2 is a 3 by 3 times a 3 by 6, so it'll be a 3 by 6. 3 by 4 will be a 6 by 2 by a 2 by 4, so it'll be a 6 by 4. So the cost of multiplying a 3 by 6 and a 6 by 4 will be 3 times 6 times 4. And that is equal to 174. Cool. So let's look at this last option. So A1, A2, A3, we can look at M13. That is just 54. A4 is just 0. And the cost of multiplying them together, A1, A2, A3, so that is a 3 by 3 by a 3 by 6 times a 6 by 2. So just these outer ones here. So it'll be a 3 by 2 times a 2 by 4. So it'll be 3 times 2 times 4. And that is just equal to 78. Cool. So looking at these three, so we can see that 78 is the minimum of these. So we can put 78 in M14. Wonderful. Okay, so now looking at this S matrix, so now we need to signify what number or what matrix we split up to get the minimum value. So looking here, we split it by A3, so we can put 3 in here. Okay, so now that we've filled out these two matrices, matrix M and matrix S, what does this actually tell us? So, so we can look at these and we can look at matrix S to determine where to split up this sequence in order to get the minimum amount of multiplications. So, we start by looking at the top right corner of S, so S14, so that's 3. So, that tells us that we can put a parentheses here and split A1, A2, A3 from A4. Cool. So now we need to figure out what the best way to segment A1, A2, A3 is. So with that, we can look at S13. So S13 is 1. So what that tells us is we can put a parentheses around A1. And now we have A2 and A3 left. There's only one way to multiply it together. So we can just put a parentheses around them like that. Cool. So the final result with the minimum amount of multiplications, the most optimal way is to multiply A2 times A3, and then multiply that by A1, and then multiply that by A4. So let's draw this out. So let's write A1, A2, A3, and A4. So let's kind of draw in like a tree. So first, let's multiply A2 and A3 together. So that's the first. And then we'll take this result and multiply this with A1. So we can draw this here. And then from here, we can multiply all of that with A4. And that is our final result in the most optimal way. So we've completed the matrix chain algorithm for this simple example, and we have concluded this. So it uses dynamic programming and solves the small problems and uses the answers to the small problems to solve the bigger problems all the way until you solve the finished one.
Thanks, Ethan. So let's take a look at what actually goes on during this algorithm and kind of take ourselves step by step through it. So the first thing we're going to do is instantiate our two matrices of size n by n, with n being the number of matrices we're multiplying and we're solving for in this case. That first matrix, matrix M, is going to save the cost of multiplying two of the given matrices together. So again, kind of like Ethan displayed in his demonstration, it's going to look sort of like that half-filled matrix with a series of zeros all the way across the diagonal, across the even index diagonal, where it's 0, 0, 1, 1, 2, 2, and so on. And then the next column and the next sort of diagonal being the cost of multiplying two matrices together, 3 matrices, 4 matrices, all the way until we're up to our final sort of index, all the way up to our rightmost corner, which is our overall cost. Now, where dynamic programming comes in and really where our runtime efficiency comes is in our second matrix, matrix S. What matrix S does is it saves the partition for minimized cost. What does that mean? So when we're multiplying two matrices together, say it's matrix 1 and matrix 2, in order to have the minimum number of equations, you put the parentheses or the multiplication sign the only place you can, right after matrix 1. What matrix S saves is it saves the matrix index at which the biggest parenthesis is going to be taking place. So if you're multiplying a series of matrices 1 through 4, and the most efficient manner is to put the biggest parenthesis after the series 2 to 4, or in the series 2 to 4, that initial partition is going to be at matrix 1. So we're going to put a 1 in matrix S, and then continue to calculate the costs working backwards, using our smaller solutions to solve for the larger problem. Now, this is done through 2 for loops where we kind of work our way down into our most basic cases, the first one being the series of zeros, the second one being multiplying one matrix by one matrix, so we have that base, obviously filling in matrix S as we go. As we continue to work up into larger series, this is where dynamic programming comes into play. As we get into a cell where we're multiplying a series of matrices, we work backwards by finding the matrix with the matrix series with the minimum cost associated with, or the series that multiplied then all the way out has the minimum cost, that partition being continually saved in S. So as we work into larger series and larger numbers of multiplications that need to happen, we can trace backwards and use our dynamic programming, our smaller solutions, to create a larger solution. So as that works, we begin to test each possible combination of matrices using the references saved in S and M, while saving the path with the lowest cost of insertion all the way up until we get into that upper rightmost corner of both matrices. This upper rightmost corner represents the overall equation and the overall problem that we were trying to solve. The way that kind of we can then return that is by returning the number stored in the upper rightmost corner of matrix M, which is our overall cost, our overall minimized cost of running this multiplication. And then in matrix S, we can return sort of the back tracing of where our partitions need to be. That upper rightmost corner tells us where our first parenthesis, our first partition needs to be. We then go back to that partition, go n plus 1, and just continue to work backwards until we're down to a very small number, or essentially just one matrix that then gets multiplied by the next one and the next one and so forth. Now, what is the runtime and efficiency of this algorithm? So the first thing I want to look at is just the naive approach, the brute force approach. What this does is it tests all possible means of parenthesizing and possible combinations that we could have to find the most efficient, the minimized number of calculations. It's an incredibly inefficient algorithm. And the reason is because you're going to have constant redundant calculations and constant redundant iterations through the matrices. The reason that this exists is because there are n minus 1 possible ways of parenthesizing the multiplications at each level. So what that means is if we're multiplying two matrices, there's one way to put the parentheses around each matrix. Excuse me. Now, what that does is it creates two partitions with a left number of elements and a right number of elements. There are also n minus 1 number of ways to parenthesize your right equation as there are your left equation. What this gives us is a number of it gives us r minus 1 times l minus 1 possibilities or possible combinations that we have to test for each of the n minus 1 combinations at the level above it. This ends up in an this ends up exponentiating itself as you begin to add more and more matrices to this equation. Overall, this gives us a ridiculous amount of redundant calculations. It finds us the right solution, but at the cost of an immense amount of runtime. So let's look at the optimal solution. The optimal solution comes through dynamic programming, and it comes through a half-filled table of size n by n. Now, we're going to need to calculate this as a big O of n squared elements used in the table. The reason for that is that you've got a total box that's n squared big that you're only filling half of. That's n times n minus 1, n plus 1. If we put in the series of zeros, divided by 2, which the 2 for the purposes of runtime isn't a significant enough denominator, where it actually changes the fact that we're n squared plus n. So we end up with an n squared calculation of the value in each space. What that's done is that's through two iterative for loops to work our way through the diagonals of each level of matrices M and S. The next step within this problem is the actual calculation and the time to fill each cell in the big O of n squared box. That takes one loop and one iteration through a worst case of n, or the number of possible matrices you would be multiplying. And the reason for that is that we're diving back into our saved multiplications, into our saved minimizations that allow us to effectively and efficiently partition the matrices in a manner that we only have to do the calculations, branching off from that initial series of two matrices that we've partitioned into. Overall, this gives us 3 loops, 2 iterative loops, and 1 calculative loop that ends up in a big O of n times big O of n squared, which gives us big O of n cubed as our overall runtime for matrix chain multiplication. Now, in conclusion, the matrix chain multiplication algorithm, it finds the most efficient way to multiply a series of matrices together. It doesn't actually do the multiplication, but working into that multiplication, it minimizes the amount of time it will take in order to conduct that multiplication and saves you from a brute force series of multiplications into a dynamically programmed, much more efficient multiplication than you otherwise would have had. This algorithm is going to return your overall cost, which again is that upper rightmost cell in your matrix M, which stores costs per calculation, as well as the partitions required for cost, which could be returned very simply in a list that's found by backtracing through your matrix S, starting at the upper rightmost corner and working back through the multiple partitions required. This algorithm operates in a cubic efficiency, which is done by eliminating the number of redundant operations we have in our naive algorithm by essentially by using dynamic programming and not unnecessarily traversing and doing multiplications twice. I just want to take a minute to say thank you again for a phenomenal semester and for everything you've taught us, Professor Liu. I'm very much looking forward to the next semester in the spring. Thank you very much, and it's our presentation.